students?
Sir, shall I
invite
start?
Badusha to lead this session.
Okay, sir. Shall I start?
Okay.
Sir, how many members are in this chat?
Only 11 members are there. 12 members are there, including me. Only 11 students are there in this group now. But I think this is the initial class so that we can start the class right now.
Sir, the time is already 10 minutes late. So
you please start the class.
Okay, sir. Okay. Good morning, friends. Today we are discussing about the third unit, that is harmonic functions. So I invite all of you to this class. I divide the portion. I took the portion of introduction to harmonic analysis, harmonic function. So Arshin, Swetha, Sreya and Anisha will take the class. So I invite Arshin. First, I invite Arshin to this class. Arshin, please start now.
Okay. Sir, can I start presentation?
Yes, Arshin. Hello. You can share the screen, then start presentation.
Okay, sir. Sir, is it visible?
Yes, this is visible, but if you put your mobile phone in a horizontal position, that will be good, I think.
Okay, sir.
Okay, very good.
Okay.
So, our first section is Module 3, Harmonic Functions. Section 1.1, Basic Properties of Harmonic Functions. We begin by recalling the following definition and giving some examples of harmonic functions. Definition 1.1.1. If G is an open subset of C, then a function u from G to R is harmonic if u has a continuous second partial derivatives and it satisfies Laplace equation. Laplace equation is dou square u by dou x square plus dou square u by dou y square equal to 0. So, a function u of s comma y is called harmonic if it is twice continuously differentiable and satisfies the following partial differential equation. That is, dou square u equal to uxx plus uyy equal to 0. This equation is called Laplace equation. So, a function is harmonic if it satisfies Laplace equation. Here the operator del square is called Laplacian and del square u is called Laplacian of u. The next remark says that a function f on a region G is analytic if and only if real part of f equal to u and imaginary part of f equal to v are harmonic functions which satisfy Cauchy-Riemann equations. Cauchy-Riemann equations is dou u by dou x equal to dou u by dou y and dou u by dou y equal to minus dou v by dou x. We have a theorem that a function f of z equal to u plus iv is analytic in a domain D if and only if at every point in D the first partial derivatives of u and v exist and are continuous and satisfy Cauchy-Riemann equations. Then we prove that this satisfies Laplace equation. Then only the function is harmonic. Here, by taking partial derivative again with respect to x in ux equal
Arshin, 1 minute.
Sir?
Dear students, you can intervene whenever you need a clarification or if you find that the explanation given by the person who is handling the session is in a wrong way, you can intervene. No problem. Okay?
Okay, sir.
So you continue, Mr. Arshin.
Okay, sir. Okay. So here we Here we take partial derivative again with respect to x in ux equal to vy. Then we get uxx equal to uyx. Likewise, by taking partial derivative with respect to y in uy equal to minus vx, we get uyy equal to minus vxy. Since vxy equal to vyx, we get uxx plus uyy equal to vyx minus vxy, which is equal to 0. So this satisfies Laplace equation. Therefore, u is harmonic. Similarly, we can handle v similarly. The next remark says that a region G is simply connected if and only if for each harmonic function u on G, there is a harmonic function v on G such that f equal to u plus iv is analytic on G. We have an open connected set G is simply connected if and only if every closed rectifier curve in G is homotopic to 0. So this remark is by using a theorem which says that if G is an open connected subset of C, then G is simply connected if and only if for each harmonic function u on G, there is a harmonic function v on G such that f equal to u plus iv is analytic on G. Next definition 1.1.4. It says that if u and v are the real and imaginary parts of an analytic function, then we say that u and v are harmonic conjugates. Also, we have a note that if f of z equal to u plus iv is analytic, then so is I into f of z equal to minus v plus iu. So, if u and v are harmonic conjugates, and so are u and minus v, we can say that every harmonic function on a simply connected region has a harmonic conjugate. This is very clear by previous two results, since we have a region G is simply connected if and only if for each harmonic function u on G, there is a harmonic function v on G such that f equal to u plus iv is analytic on G. So f is analytic means u and v are harmonic conjugates.
Arshin,
Sir,
what do you mean by harmonic conjugate locally?
sir, that's the next remark.
Yes, yes.
Next remark, sir. Okay. Next remark says that each harmonic function on a region has a harmonic conjugate locally. Here, the region G is either simply connected or not, that is, simply connected or multiply connected. If it is simply connected, clearly by the above result, our statement holds. If it is not simply connected, that is, if it is a multiply connected region, then as in figure 1.1, we can find some disk contained in it, and being a disk D, it is simply connected. So again by above result, our statement holds. That is, each harmonic function has a harmonic conjugate locally. Next remark. Harmonic conjugates of a harmonic function differ by a constant. Let v1 and v2 are both harmonic conjugates of u. Then we can write I into v1 minus v2 equal to u plus I v1 minus u plus I v2. Since v1 and v2 are harmonic conjugates of u, by definition of harmonic conjugates, clearly u plus I v1 and u plus I v2 are analytic. Since difference of two analytic function is again analytic, u plus I v1 minus u plus I v2 is also analytic. So I into v1 minus v2 is analytic. Since v1 and v2 are real, v1 minus v2 is also real valued function. Then I into v1 minus v2 is also analytic, since scalar multiple of two analytic function is also analytic. Then we have a result that real valued analytic function on a counter set is constant. So v1 minus v2 is constant. Then v1 minus v2 equal to c for some real number c. Here is a question that how can you ensure that c is a real number? If c is some complex number, then v1 minus v2 equal to c, where c is a complex number. So v1 equal to v2 plus c. This implies v1 is a complex function, which is not possible since v1 and v2 are real valued function. So c must be a real number. Thus v1 equal to v2 plus c. Next proposition says that if u from G to C is harmonic, then u is infinitely differentiable. For this, first we find the function f equal to u plus iv, that is analytic. Here, the region G is either simply connected or multiply connected. If it is simply connected, then we have a result that a region G is simply connected if and only if for each harmonic function u on G, there is a harmonic function v on G such that f equal to u plus iv is analytic. If it is multiply connected, then fix z0 equal to x0 plus I y0 belongs to G, and choose delta such that b of z0 delta subset of G. This is possible because G is open and hence z0 belongs to U is an interior point of G. So even if G is multiply connected, the ball B of z0 delta is simply connected and U has a harmonic conjugate V on B of z0 delta. So in both the cases, we find an analytic function f equal to u plus iv. Since every analytic function is infinitely differentiable, f is infinitely differentiable on B of z0 delta. So u is also infinitely differentiable on B of z0 delta and z0. Since z0 is an arbitrary point on G, u is infinitely differentiable on G. So this theorem says that like analytic function, harmonic functions are also infinitely differentiable on a region. Next theorem, mean value theorem or analogous of Cauchy's integral formula. Let u from G to R be a harmonic function and let B of AR closure be a closed disk contained in G. If gamma is a circle mod z minus a equal to R, then u of a equal to 1 by 2 pi integral 0 to 2 pi u of a plus R e raised to I theta d theta, which is mainly mean value theorem, mean value property. Proof. For the proof, we first choose an open disk D such that B of AR closure subset of D subset of G. The existence of such a disk is by choosing eta equal to infimum of mod W minus A such that W belongs to del G. Then B of AR closure subset of B of A eta, and by taking D equal to B of A eta. Here the region D is simply connected, and for this we restrict the function u from G to R to this simply connected region D such that f equal to u plus iv is analytic on D and u is the real part of f. Then we apply Cauchy's integral formula. For this we find some conditions that are necessary for Cauchy's integral formula. Here the circle gamma equal to mod z minus a equal to R is contained in the open disk D. So n gamma w equal to 0 for all w in C minus D. Also, f from D to C is an analytic function. So we apply Cauchy's integral formula that n gamma a into f of a equal to 1 by 2 pi I integral gamma f of z by z minus a into dz. Here n gamma a equal to 1 with the parameterization gamma from z equal to a plus r e raised to I theta, where 0 less than or equal to theta less than or equal to 2 pi. Then we substitute z equal to a plus r e raised to I theta in the equation, and by taking real part of each side of equation, we get u of a equal to 1 by 2 pi integral 0 to 2 pi u of a plus r e raised to I theta d theta. Next definition says that a continuous function u from g to r has the mean value property if whenever b of a r closure subset of g, u of a equal to 1 by 2 pi integral 0 to 2 pi u of a plus r e raised to I theta d theta. So using this definition, the above theorem can be also says that if u is a harmonic function, then u satisfies the mean value property. Okay, sir. So my section is over.
Okay.
Sir, shall I introduce the next person?
Yes, Badusha.
I think next I introduce Mrs. Swetha Unnikrishnan. So she will continue the next portion. Swetha, please.
Okay. Sir, shall I present the screen?
Yes.
Is it visible? Hello?
Yes.
Hello?
Yes, to you start presentation.
Okay. So here we have maximum principal first version. The statement is, let G be a region and suppose that U from G to R is a continuous real valued function with mean value property. If there is a point A in G such that U of A greater than or equal to U of Z for all Z in G, then U is a constant function. So we have given a region G and U is a continuous real valued function which is defined down G, and also U has the mean value property. So let us take a point A belongs to G such that U of A greater than or equal to U of Z for all Z belongs to G. Sir?
Here you stress the point that G is a region, means it is an open connected set, isn't it?
Okay.
The region may be a simply connected region or a multiply connected region. Okay. Sometimes there will be a hole or sometimes not. But here you stress the point that here the theorem says that we are given with a region G, which means we are given with an open connected set, which is a subset of the complex plane. And we are taking a point inside. If it is possible to find a point in point A in G, such that U of A greater than or equal to U of Z for all Z in G, then U is a constant function. എന്ന് പറഞ്ഞാൽ നമ്മളൊരു ഓപ്പൺ സെറ്റ് ആകുമ്പോൾ നമ്മൾ എന്താ പ്രതീക്ഷിക്കുന്നത് പ്രത്യേകിച്ച് കോംപ്ലക്സ് സെറ്റിന്റെ സബ്സെറ്റ് ആകുമ്പോൾ the boundary is not a member of the okay. So actually the difference is that it is impossible to find a point which is not on the boundary such that U of A greater than or equal to U of Z for all Z in G. If there is such a boundary in G which with the U of A greater than or equal to U of Z for all Z in G, then U must be a constant function. Only for a constant function we can find an A in G such that this property holds. This inequality for all Z in G. Okay. Also also, there is an immediate corollary of this result is that if there is an A with the property that U of A greater than or equal to U of Z for all Z in G, and also if U is non-constant, the point A must be on the boundary of G. Okay?
Hello. Hello.
Swetha, continue.
Okay. So we have taken a point A such that U of A greater than or equal to U of Z. So we have to prove that U is a constant function. In order to prove U is a constant function, we have to show that you must assume a constant value. So it is given, the condition is for all Z belongs to G, U of A greater than or equal to U of Z. So U of Z only attains a constant value. So it is clear that U of Z take only the constant value U of A. Therefore, we have to prove that U of Z is equal to U of A for all points set in G. For this, we define a set A equal to set of all Z belongs to G such that U of Z equal to U of A. So here we have to note that the points are chosen so that the condition is in G is completely satisfied. Okay, so which means that we have to prove A is equal to G. Now, since G is a region, which means G is a connected open set, we have to prove A is both open and closed. That is, A is both open and closed and G connected. A is closed means its complement is open, and A open means its complement is closed. Here, if A is both open and closed, which means its complement is also both open and closed, which implies that G can be written as their union. And here we obtain a contradiction. Therefore, A cannot be a proper subset of G, and hence A equal to G can be easily obtained. So this is our procedure. For that, we take the set as A equal to set of all Z belongs to G such that U of Z equal to U of A. First, we prove that A is closed. Here, A can be written as set of all Z belongs to G such that Z equal to U inverse of set singleton U of A. Here, this set U of A means it is a constant in R since U is defined from G to R. Okay, therefore, U of A is a real number and it is a closed, and also U is a continuous function. It is given. Therefore, since U of A is closed, U inverse of U of A is closed in G. Okay, so by using the definition of continuity, we know open set, for an open set, its inverse image is open, and for a closed set, its inverse image is closed. Therefore, U inverse of U of A is equal to set of all sets such that U of Z equal to U of A, which is equal to A. Therefore, we get that A is closed. Now, to prove A is open. Okay, so here to prove A is open, what should we prove? That is, we have to take a point A in G and we prove that there exists a disk containing this point and is a subset of A. Okay, so here we are going through the contradiction method. That is, we are assuming there does not exist such a disk. Okay, for that, we let set naught, a point set naught belongs to A, and we choose an R so that B closure of set naught R subset G. And this is possible because U is a function with mean value property. So only we are choosing an R such that B closure of set naught R is a subset G. So we have said that we are using the contradiction method. So we'll assume that B closure of set naught R is not a subset of G, which implies that there exists a B belongs to B closure set naught R such that B does not belongs to A. So by the definition of A, it implies that U of B not equal to U of A. That is, U of B is less than U of A, because our assumption was for all point in Z in G, U of Z is less than or equal to U of A. So surely u of b is less than u of a. And by using the continuity, u of z is less than u of a, which is equal to u of z naught can be taken. Okay, that is, we get u of z is less than u of a for any point z in the neighborhood of b. And now u of a is equal to u of z naught belongs to a is also satisfied. Okay, so we get that for any point z in the neighborhood of b, u of z is less than u of a, which is equal to u of z naught. Okay, so this can be written in another way. That is, if rho equal to mod z naught minus b, a circle is taken where b equal to z naught plus rho e raised to I theta, 0 less than or equal to theta less than 2 pi. Here we can find an interval which satisfies the condition u of z naught plus rho e raised to I theta less than u of z naught for all theta belongs to I. Because if we take any point in the neighborhood of P, u of z is less than u of z naught. So we can write u of z naught plus rho e raised to I theta is less than u of z naught. And here it is given u satisfies the mean value property. Therefore, by the definition of mean value property, u of z naught is equal to 1 by 2 pi 0 to 2 pi u of z naught plus rho e raised to I theta d theta. So, where u of z naught plus rho e raised to I theta is less than u of z naught. Therefore, what we get? U of z naught is less than u of z naught, which is a contradiction. Since we have assumed that B closure of Z naught R is not a subset of A. Therefore, the only possibility is B closure of Z naught R subset A, which implies A is open. Okay. So, since G is connected, A cannot be a proper subset of G. Therefore, A is equal to G. That is, for all point in G, U of Z is equal to U of A is satisfied, which implies that U is a constant function. Okay, so for a given U of Z less than or equal to U of A for all Z belongs to G, and U is a continuous real valued function with mean value property implies that U is a constant function. That is, U attains the value U of A. This is the maximum principle first version. Okay.
Okay, Swetha. Thank you for your cooperation. I think all of you understood the portions taken by Arshin, Rajeev and Swetha Unnikrishnan. Now I introduce Mrs. Anisha Aneesh Keke to take the maximum principle second version. Anisha, please.
Okay. Screen visible ആണോ?
Visible.
Now we are going to prove the maximum principle second version. Let G be a region and let U and V be two continuous real valued functions on G, and it also that have the mean value property. If for each A in extended boundary del infinity of G and a limit is set and limit superior of V of Z as Z approaches to A less than or equal to limit inferior of V of Z as Z approaches to A, then either U of Z is strictly less than V of Z for all Z belongs to G or U equal to V. This is our statement, and now we are going to prove the theorem. Here, first we have to understand what is the limit superior of U of Z as such Z approaches to A. It is given that it is equal to limit R tends to 0 plus supremum of U of Z, Z belongs to G intersection B of AR. And the limit inferior of V of Z as Z approaches to A is equal to limit R tends to 0 plus infimum of set V of Z such that Z belongs to G intersection B of AR. Here there is a mistake that limit R tends to 0 plus infimum and the set in set there is a supremum of V of Z. There is no need for the supremum. The definition is that limit R tends to 0 plus infimum of V of Z where Z belongs to G intersection B of AR. And now by assumption for each A belongs to del infinity of G, we have that by assumption we have the limit superior of V of Z as Z approaches to A is less than or equal to limit inferior of V of Z as Z approaches to A. Then we put the definitions into this assumption, that is we will get limit R tends to 0 plus supremum of V of Z such that Z belongs to G intersection B of AR minus limit R tends to 0 plus infimum of V of Z such that Z belongs to G intersection B of AR is less than or equal to 0. Then we fix a point A in del infinity of G, and for each delta greater than 0, let G delta equal to G intersection B of A delta. Then by our assumption, that is the inequality, we get that limit delta tends to 0, supremum of V of Z such that Z belongs to G delta minus infimum of V of Z such that Z belongs to G delta is greater than or equal to 0. And also we have the property that minus infimum of S is equal to supremum of minus S for any subset S of R. So we can apply this result into our above inequality. Then we will get limit delta tends to 0, supremum of U of Z such that Z belongs to G delta plus supremum of minus V of Z such that Z belongs to G delta is greater than or equal to 0. Then we use the supremum property that supremum of A plus supremum of B is greater than or equal to supremum of A plus B for any subset A and B of R. Then it will leads that limit delta tends to 0, supremum of U of Z minus V of Z such that Z belongs to G delta is greater than or equal to 0. That is, we get for each A belongs to del infinity of G and delta greater than 0, limit delta tends to 0, supremum of U of Z minus V of Z such that Z belongs to G delta is less than or equal to 0. Is it okay?
Okay.
Swetha?
Continue.
Okay. That is, we get that limit Z tends to A, supremum of U of Z minus V of Z is less than or equal to 0 for each A belongs to del infinity of G. So, it is sufficient to prove the theorem under the assumption that V of Z equal to 0 for all Z in G. That is, we prove the theorem by taking an assumption that V of Z is equal to 0 for all Z in G. Then it will leads to that limit superior of U of Z as Z tends to as Z approaches to A is less than or equal to 0 for all A belongs to del infinity of G from the above inequality. That we obtained from the above inequality, and we show that U of Z is strictly less than 0 for all Z belongs to G or U identically equal to 0. This is our aim, that we prove either U of Z is less than 0 for all Z belongs to G or U identically equal to 0. By virtue of the first version of the maximum principle, it is sufficient to show that U of Z is less than or equal to 0 for all Z belongs to G. Why? That is, we prove that U of Z is less than or equal to 0. In order to prove that U of Z is less than 0 for all Z belongs to G or U identically equal to 0, we prove that U of Z is less than or equal to 0. Once we proved U of Z is less than or equal to 0 for all Z belongs to G, leads to two cases. Case 1 is that U of Z is less than 0 for all Z belongs to G. Case 1. Case 1, U of Z is less than 0 for all Z belongs to G, then there is nothing to prove since we have the assumption that V of Z is equal to 0 for all Z in G. Thus, so from if once we proved u of z is less than or equal to 0, then we will obtain u of z is less than 0 for all z belongs to G. Then there is nothing to prove. And case 2 is that u of z not equal to 0 for some z not belongs to G. Then it is obvious that u of z not is greater than or equal to u of z for all z belongs to G. Then we use the hence by the first version of the maximum principle, u is constant function. That is, we get a point in G z naught. That is a point z naught such that u of z naught is greater than or equal to u of z for all z belongs to G. Then we can use the then by the first version of the maximum principle, u must be a constant function. That is, since z naught belongs to G, it follows that for all z belongs to G, u of z equal to u of z naught equal to 0. That is, u identically equal to 0. So once we prove that u of z is less than or equal to 0, we obtain these conditions. So now our aim is that we have to prove that u of z is less than or equal to 0 for all z belongs to G. And we suppose that u satisfies the condition 1.6. What is the condition 1.6? Is that limit superior of u of z as z approaches to a is less than or equal to 0. And there is a point B belongs to G with u of B is greater than 0. Then we will reach a contradiction. This is our procedure. And since u of B is greater than 0, it is possible to find an epsilon greater than 0 such that u of B is greater than epsilon. With this epsilon, we define a set capital B as set of all z belongs to G such that u of z is greater than or equal to epsilon. That is we define a new set B. That is, B is equal to set of points in G such that u of z is greater than or equal to epsilon. Am I audible, Swetha?
Yes.
Okay. Then if A be a point in del infinity of G, then 1.6 implies that there is a delta such that delta depends only on A such that u of z is less than epsilon for all z belongs to G intersection B of A delta. Since the extended complex plane is compact, by the Lebesgue covering lemma, for any open cover script U for the extended complex plane, there is an epsilon greater than 0 such that for any x belongs to X, there exists V belongs to script U such that B of X delta subset of V. In the present discussion, adjoining some more open sets to set of G intersection B of A delta such that A belongs to del infinity of G, we will get an open cover script U for the extended complex plane. That is, we are adjoining some more open sets to the set of all G intersection B of A delta where A belongs to del infinity of G, and such that this set covers the entire complex plane, extended complex plane. Then by Lebesgue covering lemma, there is an delta greater than 0 independent of the choice of the points on the extended complex plane such that in particular for any A belongs to del infinity of G, u of z is less than epsilon for all z belongs to G intersection B of A delta. That is, u of z is less than epsilon for all z belongs to G intersection B of A delta. As d of z comma del infinity of G is equal to the infimum of set of all d of z w such that w belongs to del infinity of G, which is less than d of zw for all w belongs to del infinity of G. This is our the definition, and it follows that if z belongs to G and d of z del infinity of G is less than delta, then z belongs to G and d of z comma w is less than delta for some w belongs to del infinity of G, so that z belongs to G intersection B of w delta for some w belongs to del infinity of G. Hence, by the choice of delta, we have u of z is less than epsilon. Then we will get z belongs to G and d of z del infinity of G is less than delta implies u of z is less than epsilon. That is, we get an implications like that P implies Q. And we know that P implies Q is equivalent to say that not Q implies not P. That is the contrapositive. Thus, we take the contrapositive u of z not less than epsilon is implies z does not belongs to G, or d of z del infinity of G not less than delta. That is, we get u of z not less than epsilon. That means and z belongs to G. and this will means that z belongs to G and u of z is greater than or equal to epsilon, which implies that d of z del infinity of G is not less than delta, means d of z comma del infinity of G is greater than or equal to delta, so that we get B subset of set of all z belongs to G such that d of z comma del infinity of G greater than or equal to delta. Thus our main here we want to say that B is bounded, and then also we prove that B is a closed set, that then we will arrive at that B is bounded and closed, then we can say that it is a compact set. That is our procedure. That's that from this we get that B is bounded. And there is an extra detail: if G is bounded, B is also bounded. If G is not bounded, then infinity belongs to del infinity of G, and d of z comma del infinity of G is greater than or equal to delta, implies d of z comma infinity is greater than or equal to delta. So we have that in C infinity, the metric we use some metric defined as d of z infinity is equal to 2 divided by 1 plus mod z square all raised to 1 by 2. That is, in C infinity, the metric is like this. So thus we get 2 divided by 1 plus mod z square all raised to 1 by 2 is greater than or equal to delta, implies 2 by delta is greater than or equal to 1 plus mod z square all raised to 1 by 2. And this all implies that 4 by delta square is greater than or equal to 1 plus mod z square, which implies 4 by delta square is greater minus 1 is greater than or equal to mod z square. Thus we get that root of 4 divided by delta square minus 1 is greater than or equal to mod z. Thus B subset of set of all z belongs to G such that d of z comma del infinity of G is greater than or equal to delta, which is a subset of set of all z belongs to G such that mod z less than or equal to root of 4 by delta square minus 1. So we can say that here the B is a subset of this set. So B is a bounded. Now to say that B is a closed, we know that since U is a continuous real valued function, since and also closed epsilon infinity is a closed subset of R, then we know that U inverse of closed epsilon infinity must be a closed set, since we know that continuous image inverse of a continuous um, we know that inverse of a continuous image of a closed set is closed. So B is a closed. Now being a here that thus we get that B is both closed and bounded. Hence B is compact. So if B is a non-empty, then B contains at least one point. Moreover, the continuous function U assumes its maximum at a point set naught on the compact set B, so that U of z less than or equal to U of z naught for all z belongs to B. So by the definition of B, we know that B equal to set of all z belongs to G such that U of z greater than or equal to epsilon. So that U of z is less than epsilon for all z belongs to B complement G minus B. From this we get that U of z less than or equal to maximum of U of z naught epsilon, which is equal to U of z naught, because U of z naught is U of z is greater than or equal to epsilon for all z belongs to B. This gives that U assumes a maximum value at a point in G. Such a point in set not obtained above, and it belongs to the set B. Note that for any point in G minus B, its U value is less than or equal to the maximum value U of set naught. So by the maximum principle first version, U must be a constant. But this constant must be U of set naught, which is a positive, and this contradicts the 1.6. 1.6 is that limit superior of U of z is less than or equal to 0 as z approaches to a. Hence our proof.
Anisha,
Hello sir.
what is del infinity G?
Del infinity G, if G is a bounded set, then del infinity of G is equal to del G, and if G is an unbounded set, then del infinity of G is equal to del G union singleton infinity.
Suppose G is the entire complex plane, then what is del infinity G?
G is an entire complex plane. G is equal to C infinity, then del infinity C infinity.
That is the notation. I am asking what is that set?
The infinity.
The singleton set infinity.
Singleton set infinity.
Okay. Suppose I consider the region in the first octant. What is the del infinity G?
Sir, G equal to infinity.
What is the del infinity G? Suppose I take G as the region in the first octant. First, not the first quadrant. Sorry, not octant. First quadrant. Okay. That means we are considering a real part greater than 0 and imaginary part greater than 0. That portion. What is the del infinity G?
It's unbounded. Infinity union. The infinity union pinna second quadrant, third and fourth.
No.
Infinity union real part of set of all set such that real part of set greater than or equal to 0 and imaginary part of set greater than or equal to 0. And then full region will infinity matra because sir.
It is actually the positive real axis, negative positive imaginary axis, union singleton set infinity, I think.
Okay. Okay, sir.
Are you clear about the definition of limit to superior used when set approaches A?
Okay. That is, we are considering the limit superior of U of Z as Z approaches to A means we take a very small neighborhood, very small disk centered at A and take some and there in that disk there may be some points in G, and we will take the corresponding values of U at that points and we will take the suprema.
Please repeat.
Limit superior of U of Z as Z approaches to A means we take a very small, sufficiently small neighborhood of A, and the points that has the intersection with G, and we will consider points, consider the values of U at that points and take the suprema.
Okay, then we will get a complex number or real number. Which one?
Real number. Here we are considering.
Function also we will get a real number, isn't it?
Okay.
Then considering all possible such a radiuses are greater than 0, what we do is we consider all such superior values. So we will get a set of real numbers. Okay?
Okay.
And we take what one? What is limit to superior actually? We take the limit of such values. Okay? Okay. And you also compare this one with the limit to superior of a sequence also. Okay?
Okay, sir. Okay.
And it is an assignment for you, so you go through the discussion of limit to superior of a sequence and you compare that. That is a special case of the discussion here. Okay?
Okay.
Yeah.
Okay, thank you, Anisha. Sir, shall I call the next person? Sir. Now I invite Mrs. Sreya M. Sreya, please start the class.
Okay. Is it visible?
Yes, yes, yes.
Next is a corollary. The statement is, let G be a bounded region and suppose that W from G closure continuous function that satisfies the mean value property on G. That is, if U and V are two continuous real valued functions on G that have the mean value property, and for each point A belongs to del G. In the statement of maximum principle second version, it is del infinity G. For A belongs to del infinity G. But here, since G is bounded, the extended boundary is equal to the boundary of G. Therefore, for each point A belongs to del G, limit z tends to a supremum of P of z less than or equal to limit z tends to a infimum of P of z. Then either U of z less than V of z for all z belongs to G, or U equal to V. Here we have, from the statement of the corollary, W is a continuous real valued function that have the mean value property. Also we have the real valued zero function 0 from G to R defined by 0 of z equal to 0 for z belongs to G is also a continuous real valued function that have the mean value property. Therefore, A belongs to del G, we get limit z tends to a supremum of W of z less than or equal to limit z tends to a infimum of 0 of z. Since W of z equal to 0 for all z in the boundary of G, and here A belongs to boundary of C. Therefore, as z tends to A, the left hand side of this inequality tends to 0. Also, the right hand side is 0 since 0 of z is a 0 function. And also, limit z tends to a supremum of 0 of z less than or equal to limit z tends to a infimum of W of z. Therefore, the condition of maximum principle second version are satisfied. Therefore, case 1, we take first U equal to W and V equal to 0. Therefore, we get W of z less than 0 for all z belongs to G, or W of z equal to 0 for all z belongs to G. Now take U equal to 0 and V equal to W. Then either W of z greater than 0 for all z belongs to G, or W of z equal to 0 for all z belongs to G. Since both of the above cases hold, W of z equal to 0 for all z belongs to G. Hence the proof. Since we have already W of z equal to 0 for all z belongs to del G. Therefore, since G closure equal to G union del G, we get W of z equal to 0 for all z belongs to G closure. That is W identically equal to 0.
Shweta, what is the statement of the corollary? Final portion.
If let G be a bounded region and suppose that W from G closure to R is a continuous function that satisfies the mean value property on G. If W of z equal to 0 for all z belongs to del G, then W of z equal to 0 for all z belongs to G.
G ആണോ G closure ആണോ വേണ്ടത് ശരിക്കും?
നമ്മുടെ G ആണ് വേണ്ടത്.
പിന്നെ പ്രൂഫിൽ എങ്ങനെയാണ് G ക്ലോസ് വരെ ചെക്ക് ചെയ്യുന്നത്?
എന്നാ സാർ ചോദിച്ചു?
Zero on G closure also now, right? It is not a problem because already on the boundary our W is 0. Okay, we are here we are considering a bounded region. So del infinity G is equal to del G also. Okay. And moreover, already we have W is 0 on the boundary. So if you show that W equal to 0 on G, then automatically W is identically on G closure, no problem. Actually, in the statement of the proof, statement of the corollary, it is we are not asked to find it, or we are not asked to show that W is identically equal to 0 on G closure. But automatically it gets because already we have W equal to 0 on del G, isn't it?
Yes.
Yes. Okay. Continue, please.
Next minimum principle. The statement is let G be a region and suppose that U is a continuous real-valued function on G with the mean value property. If there is a point A belongs to G such that U of A less than or equal to U of Z for all Z belongs to G, then U is a constant function. We prove this result by two methods, by maximum principle second version and maximum principle first version. We first prove this by maximum principle second version. Take V equal to U and U of Z equal to U of A for all Z belongs to G. Therefore, the assumption of maximum principle second version are satisfied. Therefore, either U of A less than V of Z. Here V of Z is U of Z. Therefore, U of A less than U of Z for all Z belongs to G, or U of A equal to V. That is here V equal to U. Therefore, U of A equal to U. But U of A less than U of Z is not possible since first we take U of Z equal to U of A. Therefore, it immediately follows that U of A equal to U. This implies U of Z equal to U of A. This implies U is a constant function. Now, by maximum principles first version, from the statement of this minimum principle, we have there is a point A belongs to G such that U of A less than or equal to U of Z for all Z belongs to G. Therefore, minus U of A greater than or equal to minus U of Z. Therefore, by first version of maximum principle, minus U is a constant function. This clearly implies U is a constant function. So,
Okay. Why the first case is not possible? By the assumption of the statement of the present corollary?
U of Z equal to U of A. We take U of Z equal to U of A for all Z belongs to G.
Okay, so little less than U of A is not possible because by the trichotomy law of the real line, if we are given with the two real numbers, either A less than B or A greater than B or A equal to B. Here our U of A equal to U of A is the only true thing. So U of A less than U of A is false. Yeah.
Okay.
Okay, Badusha.
സാർ ഓളാ എല്ലാം കഴിഞ്ഞു.
So you wind up the session, Badusha?
സാറെല്ലാം കഴിഞ്ഞില്ലേ?
So you wind up, you conclude the session by saying that the session is finished.
Okay, sir. So thank you the 4th person who have presented the class. Okay, then we wind up the class. Thank you, everyone.
Okay, thank you all. Tomorrow's session will be most probably at 8 p.m. and the session will be led by Megha, and she mentioned the team members through the WhatsApp group today itself. Okay, Megha?
Okay, sir.
Okay, thank you all.